So here's the actual class instance layout for the previous example. As you can see, the base class B instance data appears in the offset 4 of class C's instance layout. And you can see here, it adds an ECX, a 4 to ECX. So we are almost sure that this is a call to a base class. And since the one above, the call above it, which we are not sure if it's a call to a constructor or call to a member function, is called above it. Since this is a compiler-generated code, we can't say that the previous call is also a call to another constructor. So we can safely assume that this particular class inherits from 2 base classes.
So for polymorphic classes, it is easy to identify the base classes because of the RTTI base class descriptors. So again, this is the class hierarchy descriptor for a specific class. So it will contain the number of base classes and pointer to the array of each base class for the base class descriptors. So here's an example. So to determine the basis for class C, you will just need to follow the VF table related to the class, and then find the complete object locator, and then follow the class hierarchy descriptor, and then follow the base class descriptors, and then each base class descriptor points to the base class.
Okay. Next, we're going to discuss about identifying class members. To identify virtual functions, we have to get the virtual function table. And we can do that through constructor analysis. This is the code for a constructor. And as you can see, in the highlighted line, there's a mov instruction wherein an address is copied to the first field in the class instance layout. And below that, there's also another one that is copied into offset 14 relative to the start of the class instance layout. Now, what this means is that, and if you look at the address, we can see that it contains function pointers. Of course, you have to look at the function first to know that. And you can see that there are several functions in there, and that would give us a clue onto what this is. But most of the time, this will indicate that that these addresses that were copied into the instance data layout fields are the addresses of the virtual function tables. And also note that there's another important info that we can get here, EDX plus 14. It will help us indicate the size of the previous instance of the previous base class above it. So it's 14H. It can be useful at some places. Now, here's an example of a virtual function call. Okay, the ECX, the pointer in that virtual function table pointer field is put inside EDX, and 4 is added to EDX, and that indicates that the address of the second virtual function, and then there's a call to EAX. So how do we identify non-virtual member functions? We can identify these by looking for function calls with where right before it, ECX is loaded with this pointer. But you can't. It's not it's not 100% sure. So you also first have to look inside the function and see if the ECX that was copied before is used but not initialized or not being overwritten. In that case, we are sure that this particular function is a member of the class where this pointer points to. Now, identifying class member variable. This one is actually easy. We can see here that this pointer ECX is copied to EAX, and a value is being written to it. So you can see that there's an access into the particular offset in the class instance layout. So that would give us a clue that this is offset 8 of that class instance layout is a member variable. Now, we can do all that, identifying the classes, class relationships, and the class members, but it is a very tedious and a very time-consuming task. So we did some automation of the particularly time-consuming task. It's not 100% perfect, but if we seek for perfection, we won't actually get done. So what we did was first we developed a tool in either Python, and then when the Sabre Security released i.SQL, the script that imports info from the IDB and more to a SQL server, we wrote the code in Ruby, and we'll show you a demo later. And here, why static approach? We are doing static approach because we are planning to support other platforms as well that are hard, where it's hard to do runtime analysis like Symbian. But of course, a hybrid approach may or will produce more exact results. Okay, here are some of the strategies that we use. It's good if you have RTTI info, but if not, when RTTI is not available, we resort to some heuristics to identify, to do the automation.
So the first thing that a tool can do is try to leverage RTTI if it exists. So with RTTI, you can identify the polymorphic classes, the class names, the class hierarchy, and the virtual function table and virtual functions, and the destructors and constructors of polymorphic classes. So the first thing you can do is to try to enumerate each item and in each item in the disassembly. If you can identify if for VF table, if an item is a D word, and then the item is a pointer to a code, if it tries to point to a code. And if the item is referenced by a code, so it means that this particular D word item is used for as a VF table assignment. So as I said before, the RTTI complete object locator is just below the VF table. So once you have the BF table, you will need to identify if RTTI complete object locator exists. What we try to do is try to parse the RTTI complete object locator, and then try to determine if the type descriptor it points to is valid by checking for that question mark AB prefix for the class name. And then once you did that, you will generate a new class, and then you will put the class name from the type descriptor. And then you will have the VF tables, and from the VF table, you will have the virtual functions. And then the constructors and destructors can be identified for all the functions that is referencing the virtual function table. And of course, you will have the base class from the class hierarchy descriptor. So what will happen if you don't have an RTTI? So you will only have the BF table and then the base classes are not identified yet. So class names can be automatically generated. So from functions referencing the BF table, you still don't know if the particular function is a constructor or destructor. You can try using some heuristics to identify, to segregate constructors from destructors. One of them, if the particular functions is being referenced to by a jump instruction, or a call referencing to the functions, and two instructions before that has the following form: a move and then a -1, and then LEA and then ECX. So once you have that, you can just cross out the CTORs and DTORs. You will have you had segregated that into constructors and then destructors.
To be able to do what I'm going to explain later, we devised an algorithm. It's actually graph-based. It's a very simple data flow analysis algorithm. I don't even know if you can call it data flow analysis. But what we do here is we start from a certain instruction, and we have what I call a track variable, which is the initial register or variable wherein the value you want to follow is in. And whenever it is copied, you just split the branch and do the same thing with the other branch. Follow the value and until that particular value is gone or overwritten. So basically, this is a graph wherein every node represents lines of code where the track variable contains the value that we initially track when we start the graph. So this is useful in some cases. Actually, this is loosely based on a code by Halver. I think it's from x86 RLib. I think you should check it out because there's a lot of interesting code in there. To automate constructor identification, we do the following. First, for dynamically allocated objects, we look for calls to the new operator, and we track the value returned in EAX. We use the algorithm I described earlier to track the value returned in EAX. When tracking is done, we look for the earliest call where the track register or variable is ECX, and we mark this function as constructor. Now, most of the time, the function found is simply a few instructions below the value returned in EAX, so this is probably overkill.